Okay, so today we're going to look at products and quotients of functions. So similar to what we saw back in lesson 7 with the sum and differences of functions. So to start with, just a little bit of notation here. So it says to combine two functions, f of x and g of x, we can either multiply or divide, and there is your notation. So it says we can create function h of x as the product of f of x times g of x, and you'll notice directly below it, instead of having them written side by side as f of x, g of x, you can also have it written with this f and this little dot in the center. We know that a dot in mathematics does indicate a multiplication. So when we see that f dot g of x, we know it means f of x multiplied g of x. Over there with the quotient of functions, same thing. We can produce function h of x as a division. So f of x divided by g of x. Again, we can have that denoted as f divide g of x. Okay, what's special about this? So same thing we saw back in sums and differences. The domain of the product or quotient of functions is the domain that is common to your original functions. It says the domain of a quotient of functions must have the restriction that the divisor also cannot equal 0. That is, if h of x is f of x over g of x, the values of x are such that g of x will never equal 0. So in other words, when we do create quotients of functions, we do have to sometimes consider extra restrictions in the domain. The range of a combined function, just as we saw back in lesson 7, is also determined using the graph of the combined function. Okay, so same thing we started with last time in lesson 7. We're just going to do a little bit of algebra here. It says you're going to determine h of x, which is defined as f of x multiplied g of x, as well as k of x, which is defined as f of x over g of x for each pair of functions. Okay, so let's take a look at a. So function f is defined as a linear function. Function g is also a linear function. So we'll start with function h of x. Okay, so just as it says, h of x is defined as the product of the two. So I'm just going to take the binomial 2x minus 1, multiply it by the binomial 2x minus 3. Please make sure you do have brackets around both binomials so that it does look like a product, binomial times binomial. Okay, so if we expand this out, 2x and 2x, of course, is 4x squared. Then it looks like we have 2x and negative 3, so that's negative 6x. Then on the inside, we have another negative 2x. So if we put that together, that would be negative 8x. And then negative 1 and negative 3 multiplied, positive 3. So in other words, when we took two linear functions and we multiplied them, we actually end up with a quadratic function. Okay, so I will also just indicate this here. This is now a quadratic function. And then what is special about the domain? Well, this one's domain is just an element of the reals. Now, I know it's not asking us to do this, but we do want to be a little more picky with domain this time because when we do have quotients, remember we don't want that denominator to be equal to 0. So this is a quadratic function, and specifically, what is the domain of this function? I am just going to indicate this here. X such that x is an element of the reals. Okay, makes sense. Both of the original functions were linear functions. Their domains were x is an element of the reals. We combine them together. Our domain is still x is an element of the reals. However, we now have a quadratic function. Okay, let's do function k over here. So k of x is defined as function f of x, which was given as 2x take away 1, divided by function g of x, 2x take away 3. Okay, so in other words, when we take these two linear functions, we divide them. What did we create? We now created a rational function. Okay, so this is a rational function. Now, what's special about this rational function? Obviously, we have a restriction in the denominator, meaning a restriction on the domain. Again, the original functions were x is an element of the reals, but now I do not want to be dividing by 0. So if I take a look at my domain, I'm going to have to restrict it x such that x cannot equal 3 over 2. Otherwise, x can be an element of the reals. In other words, we're taking that 2x minus 3, we're setting it to 0, and we're solving it for x. Okay, let's take a look at b. So now function f is a linear, function g is a quadratic. So let's take a look at function h. So if we create h of x, we're going to multiply 3x by negative x squared minus 4. Okay, so if we carry out that multiplication, h of x is going to be negative 3x cubed, and then it looks like we have minus a 12x. Okay, so this takes us back into what we saw in Unit 2. So this is just a cubic polynomial function. Okay, so it's a cubic polynomial function. And again, if we take a look at the domain, well, my linear function and my quadratic function were both x as an element of the reals. I combine them together with multiplication, I still have a function that's going to be x as an element of the reals. So I'll just indicate that here. So x such that x is an element of the reals. Okay, now let's create k. So what is k of x? K of x is defined as function f, which is 3x, divided by function g, which is negative x squared minus 4. Okay, now we do want to double check that that denominator does not factor. So again, similar to what you saw back in 20-1. Now, if you do pull a negative out of the denominator, and I will just put it right here, so this 3x is still here. If I pull this negative out of the denominator, do you see how we just get x squared plus 4? So in other words, there is no value of x that would make a denominator that's equal to 0. So we do not have any extra restrictions on the domain. This is a rational function. Okay, so when we do create this division, we do create a rational function. However, the domain just remains as x is an element of the reals. Okay, again, there's no value of x that would cause that denominator to be equal to 0. Okay, let's take a look at part C. So we're now going to create h of x first. H of x is the product of f of x and g of x. So I'm just going to write, we've got the square root of 4 take away x. We are multiplying it by this linear function, 5x minus 1. Now remember, way back in Unit 1, we talked about how you cannot multiply into the radical, but you can take and distribute that binomial out into the front of the radical. So in other words, I could write this as h of x is equal to 5x square root 4 take away x, and then minus 1 root 4 take away x. So if I did want to simplify it a little bit, I definitely could do that. So what have I created here? Well, by multiplying these two together, I've actually created a radical function. Okay, now we want to be careful with the domain because we know that function g does have a domain that's an element of the reals, but function f does not. Function f actually has a restricted domain. So if I take a look at that, I'll just highlight that. So remember back in 20-1, you looked at the radicand. So if you take 4 take away x and you set it greater than or equal to 0 and you start solving for x, you're going to have x less than or equal to 4. So maybe I'll just show that right here. So if I take this 4 minus x and I set it greater than or equal to 0, I would then have negative x greater than or equal to negative 4, and then I would divide the negative out, which means now, of course, it's going to flip the other way, less than or equal to 4. So that becomes my domain restriction on that combined function h. Okay, now let's create function k. So k of x is going to equal function f, which is the square root of 4 take away x, over function g, which of course is 5x take away 1. So now we have basically, it's like a radical mixed with a rational type function, but we do want to be very careful about our restriction. So let's just take a peek here. So we know that x has to be less than or equal to 4 on the radical function, but if I look at my denominator, I also have a restriction down there. So the restriction on the denominator would be that x cannot equal 1/5. Okay, so if I take a look, I'm just going to place this on a number line so everybody can kind of see what I'm talking about. So if I have x is less than or equal to 4, so if I place the 4 right here, and I think, well, if I'm going less than or equal to, it means I have to go this way. So this is basically what that domain is talking about. And then I also have this extra condition of the 1/5. Well, where would 1/5 sit on this number line? So 1/5 would sit right here. Okay, so I'm just going to put it as an open dot. Okay, so in other words, I'm not allowed to equal that 1/5, but that 1/5 is also part of x is less than or equal to 4. So in other words, I do want to include both those aspects in my restriction on my domain. So I'll just put it right here. I don't know if I have room to squish it here. I think I do. Okay, so we'll say x such that x is going to be less than or equal to 4, and I guess I'll say or actually, or x cannot be 1/5, x is an element of the reals. So we'll say or because there is actually two conditions going on there. Perfect. Okay, and then our last one here. So we first of all want to create function h. So h is the product of f and g. So we're going to take the binomial. Again, please make sure you have it in brackets. We're going to multiply by this trinomial. So here's this trinomial. Now if I go ahead and expand this out, it looks to me like we're going to get a cubic function. Okay, so what are we going to have here? We're going to have x cubed minus 8x squared plus 15x. Then we're going to have minus 3x squared plus 24x's, and then minus 45. So if I simplify this, h of x is going to be x cubed. If I join together my x squares, it looks like I have negative 11x squares. I'll join together my x's. Looks like we have positive 39x's. And then it looks like our constant is just negative 45. Okay, so in other words, the product of these two functions has created a cubic polynomial again. Okay, so same as before. So because the original two functions were domains of elements of the real, it looks like the domain for this one is going to remain x, such that x is an element of the reals. Okay, and then we'll create k of x over here. Okay, so k of x is going to be the quotient of function f, which is x minus 3, divided by function g, which is x squared minus 8x plus 15. Okay, so as we saw back in 20-1, also in our previous lesson on rationals, we do now have to factor that denominator. Okay, so I'm just going to factor it down here. Okay, so this is going to be x minus 3. On the bottom, product of 15, sum of negative 8, is going to factor into x minus 5 and x minus 3. Okay, so if I simplify this, my k of x is going to be really 1 over x minus 5. Okay, so I can simplify it all the way down, but remember that means you're going to have to attach a restriction to it. So you do have two restrictions. According to those non-permissible values, x cannot be 5 or 3. So I'll just put it right here. We are kind of running out of room here. So I'm just going to stick it right here beside it. Okay, so x cannot be 5 or 3, but there's my fully simplified of function k. Okay, so that's all that kind of basic, straightforward, just basically creating the equation based on what they asked you to do. Maybe I will indicate here again, this was a rational function that we created. Okay, so that last one was a rational. Okay, moving on to question 2 here. Okay, so now they're giving us basically what we're doing. So how are we going to combine f and g, but then they're also giving you a specific value to substitute into x. So again, very similar to what we saw in lesson 7 with our sums and differences. Okay, so if I have this f dot g of 5, what does this really mean? This means that I have f of 5, which I'm then going to multiply by g of 5. Okay, so let's substitute in. So function f is defined as this quadratic x squared plus 1, but what this means is I'm now going to substitute the 5 into the x's position. Okay, so here we go. I'm just going to use a square bracket here. Okay, so here's my substitution of 5. So 5 is going in. I'm squaring it. I'm adding 1. So there's function f of 5. Now we're going to multiply that by function g of 5. Okay, so if I multiply that by function g of 5, I have negative 2. Now sub the 5 into the x position, and there we go. Okay, so at this point, you could just go ahead and type that in your calculator, do it in your head. What do you really have here? You have 26 times negative 10. So it looks like we should get negative 260. Okay, so I'm just going to put it right here. Again, I could quickly do that in my head. Okay, let's take a look at B. So again, now they're asking for that quotient, g divide f, but specifically of negative 4. Okay, so what does this mean? This means that we need to do g of negative 4 divided by f of negative 4. Okay, so I'm going to work this way now. Okay, so let's substitute the negative 4 into function g. So function g is negative 2x, so negative 2 times negative 4 over function f, but now we're substituting a negative 4 into the x position. So here we are, replacing the negative 4 into the x position. Okay, so if I simplify this, I should have an 8 on the top, and I should end up with a 17 on the bottom. So we end up with 8 over 17. Perfect. Okay, so moving along, we're now going to take a look at what these things look like on a piece of graph paper if we start doing either the product or the quotient. So this first one here looks like it's a product. So it says function f is a linear function, x minus 3. Function g is also a linear function, x plus 1. So it says we're first of all going to determine the equation h of x, which is defined as the product f multiplied g. Okay, so here we go. So what is h of x? H of x is going to be this x minus 3 multiplied by this x plus 1. So again, make sure you've got those binomial brackets because you're now going to, of course, expand this out. So x by x is x squared, x by 1 is 1x, negative 3 by x is negative 3x. So therefore, if I simplify that up, I'm going to have minus 2x's. And then negative 3 and 1 is negative 3. Okay, so part B, well, what type of function did you create? Well, it looks like we created a quadratic. Makes sense. A linear times a linear is going to give us a quadratic function. So we now have a quadratic. Okay, perfect. And now it says we're going to sketch the graph of function f, function g, and function h on the same set of coordinate axes using a different color for each, which of course is just going to help you see it better. All right, so same as we did back in lesson 7. So you can definitely use the table of values off of your graphing calculator if you want, but you can also manually come up with these points by just subbing those x values into the corresponding function. So it really doesn't matter. But when I go to make function h, I'm going to create function h as y coordinates using the y coordinates from function f and function g. Okay, so here we go. So if I did put a negative 3 into the x position of function f, you're going to get negative 3 minus 3, you're going to get negative 6. Okay, if I place the negative 2 into the x position of function f, negative 2 minus 3 is going to be negative 5. If I place the negative 1, I'm going to get a negative 4. If I place a 0, negative 3. If I place the 1, I should get a negative 2. If I place a 2 into the x position, negative 1. If I place a 3 into the x position, I should get a 0. And if I place a 4 into the x position, I'm going to get a 1. So that was a nice simple one. Okay, so now what I'm going to do is I'm going to take that information, I'm just going to quickly graph it over here. Okay, so this is going to be the graph of the function x take away 3. All right, so negative 3, negative 6, negative 2, negative 5. It looks like we're just going to have this linear function like this. So I'll just put a bunch of dots, and then we'll connect them with a straight line. Put some more down here. Okay, so this is going to be function f. So this is f of x. Okay, now we'll create the table for function g. So again, you can either manually place those x values into the function, or you can use the table of values on your calculator. It doesn't matter. Okay, so if I put an x value of negative 3 into function g, negative 3 plus 1 is negative 2. If I put a negative 2 into the x position of function g, negative 2 plus 1 is negative 1. If I put a negative 1 into the position, I get a 0. Put a 0 into the x position, I get a 1. Put a 1 in, I'll get a 2. Put a 2 in, I'll get a 3. 3 in, I'll get a 4. A 4 in, I'll get a 5. Okay, so again, nice and simple. Let's now draw function g onto the graph paper. Okay, so negative 3, negative 2 is going to sit here. Negative 2, negative 1. So again, it looks like you have this line that is looking like this, which makes sense because the slope is equal to a 1. So that's why we have all these dots just in a row like this. Okay, so now we'll connect these. All right, so this is function g of x. Okay, so now just like I did back in lesson 7, I'm going to create function h by using f and g's y coordinates. Okay, so if this is negative 6 and this is negative 2, well, negative 6 multiply negative 2 is just going to give you positive 12. Okay, maybe I'll go over here and I'll just show like, hey, by the way, I just went negative 6 times negative 2. If I take negative 5 and negative 1, it's going to give me positive 5. So again, I'm just going to show that right here. Negative 4 and 0, if I were to multiply those together, it's going to give me a 0 here. Negative 3 times 1, well, that's going to give me negative 3. Negative 2 times 2, that's going to give me negative 4. Negative 1 times 3, that's negative 3. 0 and 4, well, that's going to give me 0. 1 times 5, well, that's going to give me 5. Okay, so in other words, I'm not going to be graphing h of x and looking at a table in my calculator. I have everything I need by just multiplying those y coordinates of f and g together. Okay, now I'm going to plot these. Okay, so I don't think my first one will fit, but my second one will. Negative 2 comma 5 is going to be placed right here. Negative 1, 0, there's my x-intercept. 0, negative 3, there we go. 1 and negative 4. Right here. 2 and negative 3. Right here. 3 and 0. And 4 and 5. So I can see the symmetry very nicely here. Okay, so now we're going to connect these. And remember, this is a quadratic, so you do want to make it look parabolic. No funny points at the bottom. It should look like a U shape at the bottom. The diploma doesn't like when you put V's where there's supposed to be U's. Okay, so this is function h of x. Perfect. Okay, then it says, what do you notice about the x and y intercepts of your product function? Remember, your product function is function h, and how they relate to the original two functions. Okay, well, let's take a look at the x-intercepts first. So this should make sense. How come the x-intercepts of the original function are also the x-intercepts of the product function? Well, if they were an x-intercept of the original function, doesn't that mean that one of them would have been a 0 on the y value? Yes, like I can highlight this here. So I see right here, this negative, when x was negative 1, g had a y value of 0. So anything multiplied by 0 is still going to have a 0 in that product function. If I look at the function f, where was the 0 on the y value? It was when the x value was equal to 3. But again, when you're making the h function, you're multiplying. So if you take that 0 and multiply it by any number, you're still going to produce a 0 in the product on the y position. So that's why we're always going to share them. So whatever the original two functions x-intercepts were, when you do a product function, that product function is going to share the exact same x-intercepts as your original two functions because of that multiplication of 0. Okay, so let's jot that down because it does ask us a question, so we'll write that down. So what do we notice? We notice the x-intercepts of h of x are the same as f of x and g of x. This is because of the multiplication of the y value of 0. Okay, so anytime we times by 0, we're still going to have that 0. Okay, now let's take a look at your y-intercept. Okay, so the y-intercept here just happens to be the same y-intercept as function f of x. But again, if you're taking a look, we know that we were multiplying to get them. So if I highlight this one here and this one here on the graph paper, well, g's y-intercept was positive 1, f's y-intercept was negative 3. So the only reason why your product function shared that y-intercept of negative 3 is because it was actually multiplied by a 1. But if function g would have had a different y-intercept, let's pretend function g had a y-intercept of 2. Well, then if you took the 2 and you multiplied it by the negative 3, your product function h would have then had a y-intercept of like negative 6. So it just so happened that this one was sharing, but the only reason it worked that way is because of how the multiplication of the two original y-intercepts actually worked. Okay, so there's not a lot to be said here. We will just indicate though, so the y-intercept of h of x is the multiplication, or we'll just say is the product of f of x and g of x y-intercepts. Okay, so there was nothing really special there. It just so happened that it was a shared y-intercept because function g had that y-intercept of 1. Okay, and state the domain and range of function h. Okay, so the domain here, It was going to just be an element of the reals. It makes sense. Remember, function g and function f both had x as an element of the reals. So the common domain is just that x is an element of the reals. When we multiply two linears, there's no extra restrictions going on. So the domain is still going to be an element of the reals. So x such that x is an element of the reals. Okay, and I'm just going to indicate here, of course, that's the common domain. Common domain of f of x and g of x. Okay, and then the range, remember the range does come from the graph. And I do notice here that my lowest y value on this function h is at -4. So we'll say y such that y is greater than or equal to -4. Y is an element of the reals. Okay, and then I will just indicate this comes from the graph. Perfect. Okay, so that's it for the product example. Now on the next page, question 4, we're going to take a look at a quotient example. So this one gives you function f. Function f is given as a quadratic. Function g is given as a linear. We're now going to come up with the quotient function h, g divided by f. Okay, so here we go. So what is h of x? H of x is going to be function g, which is this 2x plus 6. And we're going to divide it by function f, which is x squared plus x minus 6. Now it does indicate very clearly, hey, you want to make sure you keep going until you're in fully factored form. Okay, so let's go ahead and factor this out. So common factor of 2 on the top. In the denominator, it looks like we have a product of -6, a sum of +1, so we should be able to use a +3 and a -2. So x plus 3, x minus 2. Okay, check for any common factors. Yep, I definitely have a common factor. My common factor is that x plus 3. Okay, so therefore I'm going to have a 2 over an x minus 2. That's the most simplified form of this function h. Okay, now we want to be careful though, because that means we definitely have some restrictions going on here. You actually had two non-permissible values. X could not be a -3 or a +2, but because we have that common factor of x plus 3, we also have a point of discontinuity. So there's going to be a hole in this graph, along with another vertical asymptote, because you still have that non-permissible after you divided out your common factor. So I am just going to put a little comma here. We do want to be careful. We realize that x cannot be -3 or a 2, but that -3 is a point of discontinuity. So I'm also going to come down here and let's just find our point of discontinuity. So I'm just going to abbreviate this P of DC, point of discontinuity. Okay, so we're going to go ahead and we're going to substitute in. So if x is -3, so that's the value of the common factor, the x value of the common factor, well then what's true? Then we can say y is equal to 2 over -3 take away 2. So remember, you're just substituting that value of the common factor into the simplified function. Okay, so if I do that, I get this -2 over 5. Okay, so what is my point of discontinuity? My point of discontinuity is actually -3, comma, -2/5. Well, -2/5 is really just -0.4. So it's almost at the -half position when we go to graph it. Okay, so that's all really important stuff there for part A. Okay, what type of function is your quotient? Well, our quotient is definitely a rational function. So similar to what we saw back in lesson, what was that, lesson 5? Okay, so rational function. All right, so now we're going to go ahead and we're going to come up with our table of values. So again, you can either manually plug in that value of x into the x position of each function. You're also welcome to use the table of values. That's what I did for this question. I actually used the table of values. So I'm going to go ahead, I'll just fill them in for you guys. So for function f of x, here are the y values when x is -4, y is 6. Here we have a 0, a -4, a -6, -6, -4, 0, 6, and 14. Okay, so I literally took those off my table of values. Okay, I'm now going to go ahead and graph function f onto this graph paper. Okay, so here we go. So -4, +6 is going to sit here. -3, 0, -2, -4, -1, -6, 0, -6. So the vertex is going to be just a little bit below there. And then we have 1, -4, because here comes our symmetry. We're coming back up. 2, 0, 3, and 6. Okay, so the parabola is going to come like this. And that's going to be a little bit below here. And it's going to turn and come up. Again, please don't put any V shapes here. This is supposed to be a parabola. It needs to have that U shape on the bottom. Okay, so this is f of x. Okay, so same thing. Now I'm going to pull my values of function g, the y values, when x is given. Okay, so here, if I place a -4 into the x position of function g, you're getting a -2. Here you get a 0. Here you get a 2, a 4, a 6, an 8, a 10, a 12, and a 14. Okay, now I'm going to go ahead and graph function g. So function g was just a linear function. Okay, so -4, -2 is going to sit here. -3, 0. -2, +2. So there we see that slope of 2 happening now. Okay, here's another point. 0, 6 is the y-intercept. 1 and 8. And then 2 and 10. Okay, I can also put some more down here. I'm just going to put a few more dots here. Just makes it a little bit easier to draw the line. And remember, you can put those dots in because you know the slope is just a +2. Okay, so this is going to be function g. Okay, I'll label it right here. And now we're going to use the values of our y for f and g to create our function h as coordinate point. Okay, so remember it's g divided by f. Okay, so for this one, if I take -2 and I divide it by 6, well, this is just really -1/3. Here, remember, we already discovered that -3, when x was -3, remember when x was -3, you had this point of discontinuity up here. So I'm just going to put a little note here. This is the point of discontinuity. Okay, point of discontinuity. And I will just put this here, -3, -2/5. So that's going to become a hole in the graph. There's not an asymptote or anything there. There's a hole. Okay, moving along. So g divided by f. So this would be 2 over -4. So this is going to be -1/2. Okay, next one. This is going to be 4 over -6. So this is going to be -2/3. Here you would have 6 over -6. So this will be -1. Here we'll have 8 over -4, so this will be -2. Here, this is going to be 10 over 0. Okay, well, that makes sense, because didn't we say up here that our other problem was when x was 2? When x was 2, we had a non-permissible. It was your vertical asymptote. So this guy is actually undefined. This is undefined, and we know that this is going to create a vertical asymptote on our graph. Okay, moving on. 12 over 6, this is 2. And then 14 over 14, this is just a 1. So see how now we're tying everything together. Like all that stuff we learned in lesson 5 is coming back when we do these quotient functions. Okay, let's go ahead and plot these things. So the first thing I'm going to do is I am just going to put that asymptote vertically in here. That's happening when x is equal to 2. So we do have a vertical asymptote right here. I'll try to make it look a little bit thicker so everybody can see it. Okay, so this is your vertical asymptote. This is x equals 2. Okay, now if I take a look at the horizontal asymptote, okay, so let's just take a peek here. So see how you have like a degree 1 over a degree 2 polynomial way back in part A here. So remember, if we think back to lesson number 5, when you have that small degree over that bigger degree, it means that, of course, that your asymptote horizontally is just going to be sitting at 0. So I could draw that y equals 0 line in as well. Okay, so again, I'm just going to try to put a little bit darker so everybody can see it. Okay, so this is technically your horizontal guy. So you're not going to be touching that. Okay, so we want to stay on either side of it. Okay, so now let's go ahead and plot our points. So -4, -1/3. So in other words, it's going to be like super, super close to this x-axis here. You've got your point of discontinuity at -3, -2/5. So there's going to be like a hole right here. So I'll just kind of make it super big. I'll kind of magnify it here. I know it's not going to be that big for real, but there's a hole right there at -3. Okay, next one, we have -2, -1/2. Okay, so that would be going a little bit lower still. We have -1, -2/3. So again, a little bit lower still. Then we finally have 0, -1. Okay, so we finally have a coordinate point that we can actually plot. Then we have 1, -2. So that's going to sit right here. Then we have the asymptote. Okay, so I'm going to go ahead and sketch this. So in other words, this is going to run like this, just like you saw in lesson 5. Then there's going to be that hole, that break. So we're going to jump over that. Then it continues here, coming this way. And then it's going to start heading down towards this asymptote. Okay, just like we saw back in lesson number 5. Try to make this look a little bit smoother. Okay, now we're on to the right side of the vertical asymptote. So 3, 2 is going to land here. And then we had a 4, 1, which is going to land here. So again, we can see that curvature happening. So this is curving up towards the asymptote. And then this is coming down towards the x-axis. Again, we're not going to cross it because that is definitely a horizontal asymptote there. Okay, so something like that. So we've now created the graph of h of x. Okay, and then part D, what do you notice about the x and y intercepts of the quotient function and how they relate to the original two functions? Okay, well, let's talk about the x-intercepts. We kind of already had them in our table here. Okay, so what's happening to the x-intercept of function f? I'm just going to highlight it. Okay, so function f, its x-intercept was right here. Okay, it was sitting at x equals -3, but what happened on function h? Well, in function h, the x-intercept of f actually became that discontinuity, right? Because it was also the same x-intercept that g had. So notice how they both ended up with zeros here, right? So in other words, -3 was the x-intercept of f and the x-intercept of g. In other words, it was the common factor. So that common factor then becomes that point of discontinuity on our quotient function. Okay, so let's write down that one first. Okay, so we'll say the x-intercept, or we can say the shared x-intercept of -3 becomes the point of discontinuity on h of x. This is because there will be, or we'll say there is a common factor of x plus 3. Okay, so because it was a shared x-intercept, both f and g had that x-intercept. That's why we have that common factor, which of course is creating that discontinuity. Okay, what else did we notice? Okay, so that was right there. I can see all that stuff right here. See how they're all lined up? Okay, now let's take a look at the other one. So the other x-intercept would have been the 2. Okay, so when function h had a 2, so that was this one right here. Okay, so there's the x-intercept of 2, and then that caused, of course, this vertical asymptote. It caused this undefined value, so we'll also make a note about that. Okay, so we'll say the x-intercept of 2. So I'm just going to put x-intercept of 2 from f of x becomes the vertical asymptote of h of x. Okay, so in other words, it was the factor that was still in the denominator after we simplified. Okay, and then what about the y-intercept? Well, same as we saw with the other product example. The y-intercept literally just comes from the division. So if you take the g's y-intercept and you divide it by the f's y-intercept, you are just producing what you see, which was that -1. So I will just indicate that. Maybe we'll put little bullets here. Okay, so we'll just say the y-intercept of h of x comes from the division of g of x and f of x, y-intercepts. Okay, and then I will just show that. Where did we have the y-intercept? So function g was a 6 and a negative 6. Okay, so here we go. I'll just put this here. So if I take g and I divide by f, this was your 6 and this was your negative 6. So that's how you produced that negative 1 on function h. Okay, and state the domain and range. Okay, so domain and range. So we pretty much had the domain up here. I had it already beside my function. I highlighted it, or I guess I didn't highlight it. I just had it written beside my simplified function. So you have that discontinuity. In other words, that's a whole. We cannot equal that x value. And then we also had that leftover factor in the denominator, which was causing that vertical asymptote, that non-permissible. So negative 3 or 2. Okay, so x such that x cannot be negative 3 or 2. Otherwise, x can be all real numbers. Okay, and again, note that that's just extra stuff. So like if you look at the two original functions, the quadratic and the linear, they did not have any restrictions on their domain. Linear functions are elements of the reals for the domain. Quadratic functions are elements of the real for the domain. But then you start dividing them, you're creating all kinds of issues in the denominator. So in other words, these restrictions are coming strictly from the fact that you divided g by f. Okay, so they're the restrictions on the denominator. The denominator cannot be 0. Okay, and what about the range? So the range, we can take a peek at the picture. So we definitely had that restriction on the horizontal asymptote, so y cannot be 0. But then you also had that restriction on that discontinuity. That was your y value of negative 2/5. So there's two y values that we need to avoid. So we'll say y such that y cannot be negative 2/5. It also cannot be 0. That's your horizontal asymptote. Otherwise, y is an element of the reals. So a lot more going on in quotient functions because of that denominator. We have to be very careful with it. Okay, so let's take a look at the next page here. So this is similar to what you guys saw in sums and differences. So we literally are going to just take, I'm going to make a quick little table of values here so that everybody can see how the points are working. And then we're going to go ahead and sketch the new picture and then state the domain and the range. Okay, so here we go. So this one is talking about a product function. So it says h is defined as the function f multiply function g. So just like addition, the order you multiply in does not really matter. Okay, so I'm just going to start where I can see it. So for example, when x is equal to negative 8, I can definitely see these two coordinates. But do you see how if you started multiplying them, 4 and negative 6, that's way too big. Negative 24 is not going to fit on your graph paper. So in other words, we're going to start with an x value that actually does fit on the graph paper. Okay, so if x was equal to negative 6, I could probably fit that. So I think that's where I'm going to start because I see that when x is negative 6, I'm just going to put it over here. What is h actually going to give me? Okay, well, when x is negative 6, function f is a 2 and function g is a negative 4. So if I multiply that, I'm going to get negative 8. So that's going to fit on the graph paper. Moving along, if x is negative 5, f is equal to a 1. And g is equal to a negative 3. So if I multiply those, negative 3 will be the new y value. When x is negative 4, I'm going to get a 0 on f and a negative 2 on g. So that's going to multiply to a 0. When x is negative 3, I'm going to have a negative 1 multiplied by a negative 1. So that's going to give me positive 1. Okay, moving along. When x is negative 2, I'm going to have a 0 and a negative 2 multiplied. So that's going to give me 0. When x is negative 1, I'm going to have a 1 and a negative 3 multiplied. So that's going to give me negative 3. When x is equal to a 0, I'm going to have a 2 and a negative 4. So there's your y-intercept. So therefore, it looks like the new y-intercept is negative 8. Okay, moving along, when x is equal to positive 1, I have a 3 and a negative 5. So in other words, I'm going to have to stop because 3 and negative 5 is going to give you negative 15. That's outside the realm of my graph paper. Okay, so let's go ahead and plot these. Maybe I'll draw it in red here. Okay, we'll take these guys off. Okay, let's plot these points. So negative 6, negative 8 is going to be way down here. Negative 5, negative 3 is going to sit up here. Negative 4 is 0, so there's an x-intercept. See, that makes sense because we said whatever the x-intercepts are the original ones, when you make the product function, it's going to have the exact same x-intercepts as the original function. So there's that one. The other one should be at negative 2. Okay, let's keep going. Negative 3, positive 1. There's that one. Oh, here's the other x-intercept. Negative 2, 0 makes sense because we said that has to work. Negative 1, negative 3, and then 0, negative 8. So this becomes a quadratic. Again, makes sense. Do you guys see how the equations or the functions are actually given? So you've been given function f's equation and function g's equation. So it's a linear multiplied by a linear, which of course we know is going to give us a quadratic. So it makes sense that our picture is a quadratic. So this is the image of h of x. Okay, so what is the domain? Well, the domain should just be an element of the reals. Okay, notice how your two original functions also had domains that were elements of the reals. You multiply them together. There's no restrictions happening, still element of the reals. The range is coming off the picture of the graph. So if you could not clearly see that the vertex was sitting at negative 3, 1, we would have to actually create the product function and graph it on our calculator. Because remember, the ranges always come from the graph. Okay, this one I can see clearly. Y is such that y is less than or equal to 1. Y is an element of the reals. And again, you can also be using your interval notation instead of your set notation. Okay, perfect. Okay, let's take a peek at this one. So this is a quotient function. So f divided by g. So order is going to matter. There are your two functions if you want to actually take a look at it in terms of graphing it. I am just going to quickly write this here though, because function h is defined as function f, which is negative 4, over function g, which is this 2x minus 6. So in other words, if I take myself back to lesson 5, that means I should factor this 2 out here. So if I factor this 2 out here, I'm actually left with x minus 3. Now, why is that important? Well, because we don't want that denominator to be 0. So do you see how that simplified form of that equation is actually telling me that I have to have a vertical asymptote at x equals 3, which makes sense because you see how that is g's x-intercept. So g's x-intercept is sitting at 3. So therefore, I'm going to have a vertical asymptote at 3 because g is now in the bottom of the function. It is the denominator. I can't have whatever that x-intercept is. So this right now, I already know is going to be an asymptote. Okay, so let's place this guy in here. So this is going to be my vertical asymptote. I already know that. Okay, so this is x equals 3. All right, now let's go ahead. I am going to make a little table here for us again, just so everybody can clearly see what's going on. So there's my x values, and there is what they're now defining as h of x, the quotient f divided by g. Okay, so let's take a peek here. So what can I pick? Again, you want to be careful because you got to make sure it fits. Okay, so if I look where x is equal to 0, is this going to work? I think so. It might be kind of hard to plot it, but when x is 0, function f is negative 4, and function g is negative 6. So if you were to divide this, you're actually creating a 2/3 is what you're creating. Okay, let's move on. When x is equal to 1, I see that both my values are equal to negative 4. So it's like you're saying negative 4 over negative 4, so this is going to give you a positive 1. Okay, when x is equal to 2, what is function f? Function f is still negative 4. Function g is a negative 2. So therefore, this is going to give us a 2. Okay, we said when we had a 3, when x was 3, you ended up with that negative 4 over 0. So that's how you get that vertical asymptote, but there it is algebraically proving itself. Okay, now what happens when x is 4? When x is 4, your function f is still negative 4, but your function g is now a 2. So therefore, you're going to get a negative 2. Can we see any more of them? Yeah, we can see the next one. So when x is equal to a 5, your function f is still negative 4. Your function g is now a 4. So that's going to give you a negative 1. Okay, so let's plot those points in. So 0, 2/3 is kind of hard to see, but it's technically like right here somewhere. I guess it's not that hard to see. I can see it. It's like here. Okay, 1, 1 is going to sit here. What else do I have? 2, 2 is going to sit here. And then, of course, I have that asymptote. Okay, so again, if you think back to your lesson 5, this is like a small degree over a big degree. So therefore, you do also have this horizontal asymptote sitting at y equals 0. So technically, we could, of course, put this guy in here. So I am just going to put him in there quickly. So everything's connecting back to that lesson 5. And now I can see, yep, this is going to get closer and closer. I'm going to come through these points like this, and then it's going to head up towards this vertical asymptote. Okay, let's plot on the other side, the right side of the asymptote. 4, -2 is going to sit here. 5, -1 is going to sit here. So now I can see, yep, here it comes. It's coming like this. It's going to go through these 2 points, and then again head towards that horizontal asymptote. So that graph I just drew, that's the graph of h of x. Okay, so what is the domain? Well, we had one problem with the domain. That denominator was not allowing x to be a 3. So therefore x such that x cannot be a 3. X is an element of the reals. Okay, and then on the y side of things, everything was allowed. We just never ever crossed the x-axis. So therefore y could not be 0. Y such that y cannot be 0. Y is an element of the reals. Perfect. Okay, and our last example here. So this one is another quotient. So again, I'm just going to really quickly write it right here. So h of x is going to be f, which is x minus 1, over g, which is x minus 5. Okay, so right away I can tell I have a non-permissible. I have a vertical asymptote. The vertical asymptote is sitting at x equals 5. Okay, so I'm just going to draw that in right now. Okay, there's no point in delaying it. We can definitely put it in there. We know that information, same as we saw in lesson number 5. Okay, so let's pop this guy in here. Okay, and then we might as well also put in our horizontal asymptote. So if we think back to lesson number 5, you have a degree 1 polynomial over a degree 1 polynomial. So look at the leading coefficients, 1 and 1. So it looks like y equals 1 is going to be our horizontal asymptote. So let's also place that in. Okay, so here's my y equals 1 line coming in. Perfect. Okay, now I'm ready to, of course, actually go ahead and carry out the division. So again, I'm just going to make a table for you guys, just so you can kind of see how this is working. And again, this is defined as h of x again. Okay, so order of division matters. We want f divided by g. Okay, so let's see if I can have a start point here. When x is equal to -1. I think I'm going to start when x is equal to -1. So when x is equal to -1, function f is a -2, and function g is a -6. So therefore it's just going to give me a third, so super close to the y-axis. When x is equal to 0, function f is -1, function g is -5, so that's just going to give me a fifth. When x is equal to +1, what's happening? Function f is 0, and function g is -4. Well, 0 divided by -4 is just 0. Okay, when x is equal to 2, what's happening? When x is equal to 2, function f is a 1, and function g is a -3. So that's just going to be -1/3. When we have x is equal to 3, function f is a 2, function g is a -2. So that's going to give you -1. When x is a 4, what's happening? When x is a 4, f is a 3, and g is a -1, so that's going to give you -3. I'll have to do another table over here. Okay, then we have the 5, so I will just algebraically write it down here. So when x is 5, f was equal to a 4, but g was equal to a 0. So that's why you get that vertical asymptote that we already talked about. Okay, when x is 6, what's happening? F is 5, g is 1, so 5 over 1, so you get a 5. When x is 7, f is 6, and g is 2, so 6 over 2, so this is going to be 3. When x is 8, f is 7, g is 3, so 7/3. Okay, I think that will stop there because I'm not sure if any more of them are going to work. Oh, maybe they will. When x is 9, f is 8, g is 4, so 8 over 4, so that's a 2. Okay, so let's plot these points. Let's make sure it looks the way we know it's going to look. So -1 and 1/3. So -1 and 1/3 is going to sit like somewhere here. 0 and 1/5. is going to sit even closer. Okay, what 1 and 0 is going to be here. 2 and negative a third, so it's going to be like here somewhere. 3 and negative 1, so here we are, we're getting kind of that curve that's coming down that we know that's going to happen. There's 4, negative 3, and then we hit the vertical asymptote. Okay, so I'm just going to go ahead and sketch this in. So it's coming something like this. There we go. Okay, and now I'm going to go to the right side of the asymptote. Okay, so 6 and 5, that's going to sit here. 7 and 3, it's going to sit here. 8 and 7/3, so that's like 2 1/3. It's going to be like here somewhere. Okay, and then 9 and 2. So then again, this is going to come down like this, going through these points, just like that. And this is the graph of h of x. Perfect. Okay, now what is the domain of this graph? So we did say that we did have that one problem when x was 5. So x such that x cannot be 5. Otherwise, x can be all real numbers. And then we did have that issue of the horizontal asymptote. So y such that y cannot be 1. Otherwise, y is an element of the reals. And there we go. Perfect. Okay, so that's it for that section. So very similar to what you guys saw in the sums and differences. And now this next question is also very similar to what you saw in sums and differences. But now, of course, we're doing multiplications and divisions. Okay, so what is this? F times g of negative 1. Well, what is this? This is f of negative 1 multiplied g of negative 1. Okay, so let's locate those values on the graph. So f of negative 1, so here's negative 1. Function f is the line. F of negative 1 appears to be a negative 4 value. And then we're multiplying it by g of negative 1. G of negative 1 appears to be a positive 5 value. Okay, so if I multiply these together, my grand total should be negative 20. Okay, what about this one? This is saying g multiply f of 3. So then we want g of 3 multiply f of 3. So same thing. So locate g of 3. So when x is 3, function g is the quadratic. It's equal to negative 3. And then f is your linear. So when x is 3, function f has a value of 8. Okay, so if I multiply that together, I should get negative 24. Okay, now we have our quotient. So f divide g of 1. So this is equal to f of 1 divide g of 1. Okay, so let's get those values. So remember, f is the linear. So when x is 1, f has a value of 2. When g is 1, that's our quadratic. It is a value of negative 3. So it looks like our answer is just negative 2/3. Okay, last one here, g divide f of 0. So we want g of 0 divided by f of 0. Okay, so this is equal to, g is the quadratic. So when x is 0, the quadratic is equal to 0. And when x is 0, the linear function is equal to negative 1. 0 divided by anything is just, of course, 0. So nice and simple. Okay, let's take a look at 7. So this one is just asking us to determine the combined function. So it looks like we're combining 3 things together. So f is the quadratic, g is a linear, h is a radical. We're going to combine them all together into a product, it says, and then we're also going to state any restrictions we notice on x. Okay, so here we go. So y is going to equal, f is x squared. We're multiplying that by g, which is 4x take away 5, and then we're multiplying it by the radical, x minus 1. Now, can you expand this out? Yeah, I can multiply the monomial and the binomial, so I would end up with 4x cubed minus 5x squared, and then this is still multiplied by the radical x minus 1. Could you multiply it further? You could. I don't think we need to, but you definitely could. What is the restriction? Well, the restriction's on the radical. So if I take that radicand, I make it greater than or equal to 0, my restriction, of course, is going to be x greater than or equal to 1. Okay, so that would be my domain restriction. Okay, let's take a look at the next one here. So now this one is saying take g, so take 4x minus 5, multiply it onto your radical, which is the square root of x minus 1. Please make sure that your binomial is in brackets, please. In other words, it's traveling as a complete unit being multiplied by the radical. And this whole thing is divided by the function f, which of course is x squared. So could you expand this out a little more? Yeah, you could call it 4x root x minus 1 minus 5 root x minus 1. but I don't think we need to. Okay, so now here we do want to put our restriction on our radical and on our denominator. So notice that your denominator cannot be 0, and notice your radical is x greater than or equal to 1. So you guys would have did this back in 20-1. I'm just going to make a little number line here for you. Okay, so if x is greater than or equal to 1, so I'm going to put a 1 here, and I'm going to say greater than or equal, so it's going to look like this. But at the same time, we said x cannot be 0. So your 0 would be sitting here. So do you see how as long as you have that restriction of greater than or equal to 1, you're already meeting the restriction that you can't be 0. So in other words, you don't want to write both them down if you don't have to. So this one encompasses both of them if I just say x greater than or equal to 1. Okay, so then I'm just going to put a comma here. So x greater than or equal to 1 will encompass both the restrictions that I have. Perfect. Okay. And number 8 here. So it says if h of x is the product f times g, and f is given as a linear function 2 minus x, our job is then to determine g, stating any restrictions on x. Okay, so here we go. So h of x, I'm going to write down as x squared minus 2x. This is equal to f, which is given as 2 minus x multiplied by g of x. So do you guys see how all we're doing to get g of x is dividing that binomial over? Okay, so I'm just going to write over here. So therefore, g of x is really this x squared minus 2x. And then we're going to divide it by 2 minus x. So x squared minus 2x. And we're dividing this by 2 minus x. Okay, I'm actually going to go ahead and factor this down for us. So if I take a look at the top, I do notice that if I pulled a negative x out, I'm probably going to create a common factor of 2 minus x. So I'm going to pull a negative x out of my numerator, and then I would have an x plus a 2. Or sorry, a negative x plus a 2. So if I get a negative x plus a 2, then I can actually call this 2 minus x. In other words, I'm recognizing that I do have that common factor there. Okay, so now that common factor, therefore I could simplify one more time, but then wait a minute, I do have to state the restriction. What is the restriction here? Well, x cannot be a 2. So it's okay to simplify it all the way to the end, but we have to make sure we're stating that restriction. Okay, and what about this one? So now h of x is the square root of x squared minus 4. This is equal to f, which is 2 minus x, multiplied by g. Okay, so therefore what is g? G of x is going to be this radical, the square root of x squared minus 4, divided by this linear function, 2 minus x. Perfect. Okay, and then we do have to state the restriction here. So we definitely have something going on in the denominator. X cannot be a 2, okay? But in the numerator, remember you have that square root function. Okay, so you could either think about it as the graph like way back in lesson number 2, but you can also do it algebraically like we saw in lesson number 3. So maybe what I'll do is I'll just do the algebra over here. Okay, so remember you're taking that radicand, x squared minus 4, you're setting it greater than or equal to 0. Therefore, x squared is now greater than or equal to positive 4. We're now going to consider both cases of the absolute. Okay, so if I absolute value this, I now have the absolute value of x being greater than or equal to 2. Okay, so I'm square rooting it, but I know that when I square root, I have to consider positive and negative. So to encompass that, I'm going to just talk about the absolute value of x. Okay, so therefore, what's my two cases? Case 1, x is going to be greater than or equal to 2. Case 2, negative x is going to be greater than or equal to 2, which means that x is actually less than or equal to negative 2. So I'm just going to highlight these. Okay, so these are the ones I'm considering. All right, so now I'm just going to go ahead and I'm going to make a little number line here. So here's my little number line. Okay, so I've got a negative 2 and I've got a positive 2. But remember, I'm also going to add this here. X also can't be equal to 2. So that's an extra condition we do want to consider as well. Okay, so here we go. So I've got this negative 2 here. I'm allowed to equal to it. But then I have this 2 here, which I'm not allowed to equal to it. So I'm just going to put an open dot. Okay, so I have to be greater than 2. But at the same time, I have to be less than or equal to negative 2. So that number line picture I just drew us, that's going to help us state our restriction. Okay, so let's go over here. What's my restriction? X is going to be less than or equal to negative 2, or x is going to be greater than 2. So notice I've taken the equals off the 2. How come? Because your denominator has a restriction. Your denominator cannot be equal to 2, otherwise you get that 0 down there. Okay, almost done here. So now question 9, I think it's the same thing. It's saying h is now defined as f divided by g, and I've given you g, so your job is to come up with f and then state any restrictions. Okay, so here we go. So x squared plus 6x is equal to function f, which I do not know, divided by function g, which is negative 2x. Therefore, how do I find f of x? I'm just going to multiply. So f of x is going to be negative 2x multiplied by x squared plus 6x. Okay, so therefore if I multiply this out, f is going to be negative 2x cubed minus 12x squared. Okay, so it looks like we've created a cubic function for function f, therefore there's no restriction on it. So I'll just indicate here, yep, by the way, x is just going to be an element of the reals for this function f. Okay, now was there a restriction on the actual function h? Yes, function h would have a restriction because you would not be allowed to have that 0 in the denominator. So maybe I'll just specifically say this is for f of x, but then we do want to make a little note over here. So for h of x, the restriction would be x cannot be 0. Okay, because remember, you do have that denominator. You have that division of negative 2x, but it wasn't very clear what the restrictions were for, so we'll just make sure we indicate both. Okay, and the last one here, negative x take away 3 is equal to function f divided by function g, which is given as negative 2x. Okay, so therefore, if I'm solving for f of x, I would have negative 2x multiplied by negative x minus 3. So therefore, f of x is just going to give me positive 2x squared plus a 6x. So because f is a quadratic, again, this would have no restriction. X will be an element of the real specifically for f of x. And I do already have this indicated right here. Okay, so if I was looking at the function h of x as it's given in the question, there is a restriction on h of x. But the two function f's that we discovered or we determined, we don't have any restrictions on those particular ones. Okay, so that is it. And there's some practice questions for you guys at the bottom there. And so then I'll come back in the next video with the notes for lesson number 9.